Good morning, everyone. All right, we'll give it about one more minute and then we'll go ahead and get started. Can everybody hear me? I just want to make sure that the audio is working. Cool. Thank you, Mr. Pena. All right, let's go ahead and get started. I assume everybody who comes in late will be able to catch up. So one of the things that I'm afraid that we tend to do, particularly in software development, is that we teach you the tools and assume that you're going to know how to solve the problems. And it has been my experience that that doesn't necessarily follow, that knowing what a for loop is and how to write one with proper syntax doesn't really tell you when to use a for loop, when to use a while loop, those sorts of things. So for the next little bit, we're going to be talking about, particularly from writing it, real-time software application, we're going to talk about some of the things that you need to do to solve problems. And so we're going to talk about drawing control diagrams, and we're going to start on some examples, both in today's class and future classes, of how to solve particular engineering problems that are real-world problems. So Once we get through all of this stuff, we're going to design an embedded system that does these sorts of things. We're going to assume that it has a double EEPROM on it that stores data that we're gathering for some purpose. Wants an activity LED to let you know that the system is alive. It's going to be measuring temperature, and it's going to have an LED that's going to indicate if the temperature is above a set point. And obviously, to do that, we're going to have to periodically read the temperature. We also have a sensor on this device that I'm pretending to have. We're going to read ambient light from an ambient light sensor. We're going to monitor a serial report. We're going to have a serial report that we're going to send reports of issues over so that somebody can watch real time and see what's happening. And we'll implement it with a hardware watchdog timer. So this is an initial diagram that I put together of how to solve that problem. And we will go over this in much more detail later on in the class. So let's talk about some symbols. You've already seen these symbols, but let's talk about them again. Semaphores and mutexes. Binary semaphore basically is that flag that you raise that's either on or off. It's either available or not available. Counting semaphore. It's where it's like a binary semaphore, but each time you post it increments, each time you pinned it decrements. And mutexes. Mutexes are the key to protecting devices. That's how you remember that particular symbol. So we can talk about mailboxes and message queues, and we discussed already that in the TI RTOS, TI says BIOS, a mailbox and a queue are basically the same structure. The difference being that a mailbox, as I would define it, holds one item at a time, whereas a queue can hold multiple items in time that you pull out in the same order that you put them in. It's first in, first. We talked about timers and event flags. We know pretty much what those are. A timer is any time that you have something that goes off and waits for a particular period of time. An event flag, on the other hand, is basically like a group of semaphores. And you'll notice that I have this and symbol in the flag for event flags, because you can either pinned on the and, which is all of the 1 bits having to be set before the pin is successful, or you can have this set up as an or, in which case we put the vertical bar in there. That would say that if any one of these 1 bits is set, then you're off to the races. So we have on these diagrams 3 different things that we're going to talk about. So a task, which I have in the green rounded rectangle. A task is a true operating system task. So it's something that has the while forever loop and is treated by the OS as an individual task. The interrupt function, so this would be something that gets called by the hardware for an interrupt. In case you're wondering about this symbol, that is Professor Willie's very best lightning bolt. Sorry, I'm not an artist, I am an engineer. And common functions are basically functions and subroutines that you write or that are written as part of the system that are just that. They're functions. They aren't tasks, although they can be called by task, and they can generally be called by things from from many locations within whatever system design we have. This purple box with that's my rendition of a wrench. The purple box with a wrench represents a hardware device. Global variables we are representing with a hexagon. And by how we shade it, we can tell whether in this particular use of a global variable, it's going to be a read-only, a read-write, or a global that is write-only. And you say, well, what do you mean write-only? So if I'm using a particular global variable in multiple locations, I'll probably have this symbol drawn at each location where that particular global variable is used with its name in it. And if it's yellow, that means that the task accessing it only writes to that variable, never reads it. And if it's white, it means that it reads it always. So that's how you can have a write-only variable. So let's take a look at this serial port example, and we'll look at some we'll look at some things in particular. But in general, let me kind of walk you around here to see what we've got. So we have this double EEPROM, and we have some functions that we're going to be writing that write to this double EEPROM. And so we have this function that we're going to call log double EEPROM. We have a function that we're going to call read. We have a function that we're going to call erase. Those are all talking directly to this double EEPROM. I'll talk a little bit more in a bit about the logger task, but his job is to log messages to the double EEPROM and to send them out the serial port. We have this user interface task, and his job is going to be to initially send stuff out to the user port. In future classes, we'll talk about how you might be able to get some input from the user as well. But for right now, what we're talking about is that this particular thing is just operating the serial port on a read basis. We have our health task down here. Over here, we have an RGB LED that we're going to use to just blink and say that we're alive. We've got another LED over here that we're going to use to turn on when we have temperature out of whack. Much later, we'll talk about this short timeout delay and why you might want to have one of those. But we have a task here that's going to read the temperature periodically, and another one that's going to read the humidity and the light level. Both of these are talking devices that are on the I2C bus. So we have this function, these functions that perform various I2C functions. This is where we connect to the humidity sensor and the light sensor. So let's talk about, in this example, this section. And that's basically the serial connection. So we have to do something to handle the serial port. So what we're going to do is we're going to write some functions that allow other functions, other tasks to address the serial port. So from a receive standpoint, when we get a character, we're going to place it into a circular queue. Is there anyone out there? Go ahead and use the group chat. Is there anyone out here who in the group that understands what a circular queue is? Might be able to explain it to us. Okay, well, we'll talk about circular queues in a minute. So a circular queue has a finite size. So received characters, when in our particular circular queue, we are going to take the philosophy that when the queue becomes full, when we don't have room to buffer anything else, that we're just going to throw away the last incoming character. Now, it's important to make a decision on what you're going to do in that case, because let's talk about received serial ports and how they work. So there are a number of things that we can do when our buffer gets full or starts to get full. So obviously we can take what we're going to do right now, has a philosophy, which is, you know what, if for some reason that buffer gets full, characters are coming in too fast, we're just going to throw away the last character that was received. That's an absolutely valid decision. But it's also equally valid to say, hey, if I've got this queue, I'm going to throw away the character that's been in the queue the longest, and I'm going to keep the character that just came in. So you may have a system where it makes more sense to do that. That old information is just that, it's old information, and the new information that comes in, you would prefer to keep as opposed to the old information. So that's certainly a valid choice, not the one we're making in this case, but that's a valid choice. And with serial ports, there's actually a third and fourth choice, which is we could choose to implement the serial port in such a way that when we get maybe the last character, maybe the second to last character, maybe the fifth to last character, where we send out what is called an X off, which is something that you send over the serial port that is a signal to the other side that's transmitting to stop transmitting. And then when there's room in our buffer again, we can send an X on, and that tells the guy on the other side that they can start transmitting again. So theoretically, with that sort of a situation, it's kind of like hitting the pause button. With that particular situation, you could never lose a character. And of course, the fourth situation is that we could use the hardware flow control signals, ready to send and clear to send. So when you're able to receive stuff, you keep the ready to send digital signal high. And when your buffer starts to get full, you drop it low. And so the other side, if they're paying attention, will stop sending data. But at any rate, that's not what we're doing. What we're doing this time is that when the queue's full, we're just going to throw things away. We're going to use a counting semaphore to indicate that a character has been added into the queue, so that you can always look at that and see that there's something left. And we're going to interface with, we're going to create a couple of interface functions. We're going to make gets with pins and get C with pinned, two functions. And as you might imagine, those work very much like the standard C library calls. Get C with pinned is going to get the next character off of the serial port, but it's going to pin. And the same thing for gets, it's going to get a string off the port. Now, for characters that we want to transmit, we're going to place those in a circular queue as well. If there's no room in the queue, we're going to drop the character. So does anybody want to venture a guess as another way that we might be able to handle on transmission when we're trying to send a character in an RTOS environment? Is there another way other than just dropping a character that we might handle that? Anybody want to venture a guess? Okay, what about doing a pin? Is there a way that we might be able to devise that we could pin so that if somebody calls the serial transmission routine, there's not room in the buffer for what they're trying to print, we could pin. Just wait until there's room in the transmit buffer before we let that task resume. So let's take a look at how we're going to implement this. So we have these functions, get S with pinned and get C with pinned. We have our interrupt handler. So we've got receive buffer characters free. We've got an interrupt for receive buffers free, transmit buffer free. So receive buffer characters free. are basically, these are potential interrupt functions that we might have to write. We have a timer here for puts to look at our buffer status that we might want to use. And we have this lock function that's going to lock the serial port while we're doing a puts in particular, and also a pin, a put C and a put S. So that we don't intersperse messages, right? So anytime you do a put, you want to make sure you get all the characters out before the next put C executes that's associated with a different string. So let's talk a little bit about a circular queue. So in memory, a circular queue looks like just any old buffer. In this case, we've got one that has 16 entries. Okay, so think of this, here's an array. Okay, and I've got some stuff that I've already got in this queue. We're gonna, because it's a little bit easier to talk about. But conceptually, this queue is circular. So what happens is that as we put numbers into the queue, so right now our right pointer is pointing to index 7. So the next character that comes in, we're gonna put into this position, then after that, we're going to put the next character in that position, and then that one, 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 and then that one. And then in 15, now if we have another character come in, oops, after we've put something in that 15th slot, we're going to wrap around and put it back in the 0 slot, and then in that one, and then that one, and then that one. From a reading standpoint, for getting stuff out of the queue, we have this pointer that points to the next thing to read. So when I read a value out of the queue, right now I would get a 9. Then the next read would get 4. So this read pointer is going to increment every time we get something out of the queue. Then it'll read that position and that position and that position. And if my buffer were like this, so I had right at position 7 and I do my read, I'm reading, 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 and then my read pointer is going to point to the same value as my write pointer, and that indicates that the buffer is empty. Okay? Why is it that that indicates the buffer is empty? Well, my read pointer, which is where I'm going to get the next value from, is pointing to exactly the same cell that I'm going to be writing the next value from. So that's always going to mean that the buffer is empty when the read and the write pointer are pointing to the same location. Now, how can you tell if the buffer is full? So let's say that nobody read anything. So we're going to write, 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 write. Okay. Then we get ready to write again. And we're going to write, when we do the write, we're going to be pointing right here at that spot. Okay. Read is pointing here at that spot. So when we are, when the write is equal to the read, like that, when it's that one before, it's going to be, we're going to call this full. Now, there are other ways to write this. This is the simplest way to write it. The net effect of writing it this way is that you'll never shove anything into the character before the tail pointer, because we figure when we're pointing to when the right pointer is the cell before the read pointer, we're going to call the buffer full. So even though we're taking up 16 bytes here, we're actually only using 15 of them. There are other ways to write it, but if we use the other ways, then it's going to cost us more. We have to keep track of more. This is a relatively fast way, and we basically end up wasting one location. So we have this function that we're going to call put q. So that's going to put something into the buffer. So the first thing that we're going to do is we're going to check to see if the buffer is full. How do we know if the buffer is full? So if the buffer is pointing to n minus 1, n being the pointer for the read. The right pointer is pointing there, okay? Then, oh, wait a minute, we did put in the extra logic. Okay, so let's take a look at how this works. Okay. So, the right is equal to n minus 1 right here. Then we check to see if the read pointer is 0. Okay. Let's look at what I've done wrong on this flow chart. So if they are the same, we're going to return. If they are not the same, right is not equal to n minus 1. Then right is, oh, excuse me. Okay, I've misread this. Okay, n is the number of cells. So if right is pointing to the 15th character, this is for wrap. So if the right is pointing here, got 16 cells, right? It's pointing to 15. Then we look to see if read is pointing to the first one. That is the equivalent of this guy being at this spot. So that would be the equivalent of this guy being here, and in which case that is true. If it's not, so if the read is someplace else, but the right is right here, then we can return false. So that would indicate, okay, buffer full. Let's start over. Buffer full. Is the right pointer equal to, is the right pointer pointing to the very last cell? Yes, it's pointing to the very last cell. Then is the read pointer pointing to the very first cell? If it is, then we have this situation where right is here, read is here, we're at buff minus 1 effectively, and so if that's the case, then we return that true, the buffer is full. If the read pointer is anywhere else in this circle, anywhere but, keep pressing that button, anywhere but here, then the buffer is not full. So let's say the right pointer is pointing to anything but cell 15. Okay, then we look to see if the right pointer is equal to the read pointer minus 1. So is the right pointer right here, in which case our buffer is full. So we would return true. If the right pointer is pointing somewhere else, then that indicates that we return false. So let's go back to putting something on the queue. So putting something on the queue, we check to see if the buffer is full. If we are, we return an error. If we're not, then we're going to take the new character and we're going to put it in wherever the right pointer is pointing. Let's say here, okay? And then we're going to increment the right pointer, and we're going to look to see if the right pointer is pointing to not 15 but 16, because this is 16 byte value, right? Okay, so if it's pointing to basically the character that doesn't exist here in the buffer, then we're going to point it right back to the beginning. We're going to set that back to 0. And either way, we're going to say success. So keep in mind, the right pointer is going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, then 0, 1, 2, 3. So it's running around in a circle. So that's how we put something into the circular queue. Getting something from the circular queue is similar kind of an operation. So what we're going to do is that the first thing we're going to do is that we're going to say, is the read pointer equal to the right pointer? Because what we said was when the read pointer and the right pointer are the same, we are going to believe that the buffer is empty. So if the read pointer and the write pointer are equal, then there's nothing to do. We just return the empty flag, whatever that means in context of this function. But if they're not equal, then what we're going to do is we're going to get whatever is stored where the read pointer is pointing. So in this case, read pointer is pointing to character 2, to this character at index 2, which is a 9, so it's going to return a 9. We're just going to put that into return value. We're going to take the read pointer and we're going to increment it. So read is now going to go from 2 to 3. And we're going to look again to see if the read pointer is bigger than the size of the buffer. So are we pointing, we're going to point to that guy as the next character read. If it is, then we set it to 0. Again, we're wrapping back around this way. And either way, we return whatever value we took off of the queue. So that is how we're going to deal with these circular queues that we talked about in this section. Are there any questions about circular queues before we go on? So I will tell you that you will eventually write a circular queue function in C. Keep it, because you're going to use it over and over and over again. Okay, so let's talk about the logger function. And let's talk about some of the characteristics of this function. Basically, with the logger function, tasks are going to send information to be logged into the logger with 2 different calls. We're going to make a send sensors to log call, which is going to log sensor information periodically. And in case we have any errors that we have to report, we're also going to have this function that we're going to call send error to log. And that also is called by whoever needs it. Now, the task is going to try to log the data. And when it's going to wait, basically, the task is basically going to pin until somebody posts something that needs to be logged. And when it does, it's going to pop it out to both the serial port and push it into the EEPROM. So there's a potential problem here, and this is one of the problems that we can fix with the real-time kernel. The problem is that the messages can potentially come more rapidly than you can write them to the serial EEPROM. And so we have to have some way to save messages, because we don't want everything to have to wait while a message is being written. We don't want to have to stop our logging function, for instance, while we're writing an error message. That would be silly. So we have to have some way that we need, that we can queue things up so that we can log them when we get around to them on a timely basis. But keep in mind, no matter what, the philosophy here on this logger function is, although we can have moments of time where we get bottlenecked, we believe that this is going to spend most of its time just sitting around doing nothing. So let's look in detail how I've structured this. So one of the things that that we need, that takes up some memory, some sort of a buffer that needs to hold the information that we want to log in case we have more than one log message waiting. And yet somehow we have, when we're done with that message, we want to throw it, we want to be able to reuse that memory. Now, we could use malloc and free. That is certainly a valid choice in some cases. The problem with using malloc and free in an embedded system, without getting too much into the the details of memory partitioning. The problem is that when you use malloc and free, you can eventually get into a situation where a malloc won't work. And then, of course, there's always the problem of if I keep mallocing and I forget to free some things, eventually memory can get full. But it can also get parsed up in such a way that there are only small portions of memory left. And that depends on which order you let things go in. So I don't want to normally use in an embedded environment malloc and free. I want something else. So one alternative is that I can have a message queue that I use. And what I'm going to do is I'm going to have this static buffer that I'm going to create that has the buffers for all of my messages, or not all of my messages. It has buffers for as many messages as I might want to be transmitting at any given time. And what will happen is that when I get ready to send a message to the logger task, these functions, either send sensors to log or send error to log, they're going to pull an unused buffer off of this queue that I'm calling log free queue. And so it's when I do a send sensor to log, I'm going to get a buffer that I can put that message in from this queue. So it allows me to reuse buffers. And then when I get ready to send it to the logger task, so I format this buffer, and then I put it into this log message queue. The logger task is going to be looking for something to show up in the log message queue. When it sees something in the log message queue, it's going to put that message out onto the serial port, and it's also going to use these log EEPROM functions to talk to the double EEPROM, to write all the information into the double EEPROM. When it's finished writing whatever message it got off of the queue, it's going to push that buffer that it doesn't need anymore back onto the queue. So in essence, and so if I had, let's say that I had a function that called log sensor, it's going to push it's going to pull a buffer off of here, fill it up with information, push it to here, put it to the logger task. Now the logger task is merely doing these functions here, and somebody else wants to log to the sensor. So this other function is going to now get another buffer off of my log queue, off of my free queue, and he's going to push that message onto the message queue. So now there are going to be two messages sitting there, and logger task is going to finish the first one, then he's going to append on the next one, and so forth. So let me show you how that's going to work. So I have this statically created array of buffers that I've made over here. Okay, and I'm going to do a mailbox create function for two message queues. One I'm going to call free queue, and one I'm going to call message queue. So I'm just going to create those things, and then I'm going to loop through 0 to 7. So I'm going to loop through these array indexes, and for each one of these, I'm going to post a pointer to message queue 0, 1, 2, 3, 4, 5 in my mailbox free queue. So it's going to post a pointer to buff 0, pointer to buff 1, pointer to buff 2, pointer to buff 3, pointer to buff 4, pointer to buff 5, pointer to buff 6, pointer to buff 7. So now this free queue now is pointing to each one of these currently unused buffers. Now, in the meantime, I also over here, as you see, I did a mailbox create for message queue. This is the queue where I'm going to put the stuff that I want to send. And this queue is all going to be empty. We're not going to put anything in it at all yet. So let's say that Joe Schlunk decides that he's going to send a message to the message queue. So he's going to do the send function, okay? And that send function is first going to do append on the free queue. Now what that's going to do is when I append, the first entry in that queue is going to be the pointer to buff 0. So when I do append, it's going to effectively empty that cell that has that buffer, and it's going to give me that pointer to buffer. So I'm going to do a mailbox pend, and that will give me my pointer to buffer 0. I'm going to put the information that I want to post that has been sent to pend into buffer 0, and then I'm going to do a mailbox post. And that mailbox post is now going to put this pointer to buffer 0 in the message queue. So just for grins, let's do that again. So I have another function that's also going to be posting a message, and he's going to do append, which will now get this next pointer off of the free queue. It's going to put information into that buffer, and then he's going to post it to the message queue. So now I've got this message queue has 2 entries in it. All the rest are empty. And over here, my mailbox, my free queue, we've still got 6 buffers left. So now my log task is over here pending on the free queue, or on the mailbox queue. So he's sending there, pending on that, and voila, that buff 0 was there. So he's going to get, when he does that pend, he's going to pull off the pointer to buff 0. Now he can print and store all of that information. And once he's finished printing and storing that information, he can post to the mailbox queue, which is now going to take that that buff 0. We're taking buff 0 out of message queue 1, and when we do the mailbox post, it's going to post it back into that position. So now the mailbox queue has 7 entries on it. They're buff 0, buff 2, buff 3, buff 4, buff 5, buff 6, buff 7, as buff 1 is still sitting over here being pointed to in the mailbox queue. Well, the log task is going to pend again on the message queue, and that's going to get the other message that we sent. He's going to print and store that information, and then when he posts, he's going to post it back up, and now that guy ends up on the free queue. So as you can see, basically we're going to take these 2 queues back and forth and share our buffers that way. Now, one of the things that you could theoretically get buffers way out of order, but this doesn't make any difference depending on what order you push, who's got a priority, what things happen simultaneously. But at the end of the day, this method will always keep all buffers in use. So let's take a look at the flow chart for our logger task. So he's going to pend for a message in the queue, and he's going to wait for a timeout. Now, the reason for waiting for a timeout, you'll see when we write our health task, but he's going to wait for a particular period of time. If he doesn't see a message, then he's going to go over here and he's going to check in with the health task and then pend again. So we talked about this last week in the health task. Whatever we're doing for the health task to pend, we're going to wait. Oh, you know what? We better let everybody know that we're alive and that we're not stuck here doing something that we don't expect to happen. And so we're going to go in, check in with the health task, and then just loop here. So eventually, we're going to exit from the pend with a timeout, or without a timeout. We're going to exit from the pend because we've got a message. So let's see, what's wrong? So is our EEPROM full? Well, if it is, I think I'm going to want to write over my last entry in my double EEPROM, my oldest entry. because I don't want to lose my most recent information. So I'm going to overwrite the double EEPROM. The EEPROM is not full, then I'm going to store the information I just got into the double EEPROM. Then I'm going to format it into a string that's suitable for the serial port. And then I'm going to do a delay to make sure that we've got a delay for the serial port. Make sure that well, we'll see when we talk about our serial port functions why we've got that. And I look to see if there's room in the transmit buffer. So if there's not room in the transmit buffer, then I think I'm just going to check in with the health task and sit here and wait. Now, the reason for this is this delay gives time for another function to operate, and this lets us, even if the serial port is slow, to not lose things in our circular queue. So we're just going to be checking. So room in the transmit buffer, we're just going to ask if the transmit buffer is full, and if it's not, we're going to do this. So we're going to go ahead and make the decision to pause here if that is the case, until there's room in the transmit buffer for us to send the message. Then we're going to send the message to the serial port. We're going to post the buffer that we just finished using back in the free queue. We're going to check in with the health task, and we're going to pend again. Now, the top part of this, I have a function that I'm calling, I like to start things with a start task. And so to get everything kicked off, we would actually start by calling this start logger task that would create the message queues, initialize the serial port, initialize the double EEPROM, and then start the logger task. We'll see how that works in our health task later on. So one of the things that we need to think about is how are we going to do double EEPROM operations. And double EEPROMs, it's not just a matter of writing out to a double EEPROM. It takes time for certain things to happen. In particular, programming and erasing on double EEPROMs takes a finite amount of time, much longer than what would happen on a just going out the I2C port or the SPI port. So one of the things that we need to know is how long are those delays? Because we have to figure out how we're going to deal with them. And so I pulled up the data sheet for a double EEPROM here. And let's kind of take a look at some of these values. So how long does it take to program data into a double EEPROM? So this says 600 microseconds is the max for writing a 32-bit value, and that's a that's a long time in terms of CPU cycles, but it's close to a millisecond. 600 milliseconds, a millisecond. Programming time for 32 bits of data that requires copying to a buffer, and this is a condition where you have basically where you're not erasing things. And so these programming times really don't apply to what we're doing. Right now, we're looking at most of the stuff, we're always going to have space available. Most of our stuff is going to take around a millisecond. Now, what we will find is that if we can find, do I have the erase time? Yes, so the erase time, so if we have to go off and erase, the erase time is going to take most of the time, if we have, for a mass erase, it's going to take somewhere around 15 to 500 milliseconds, depending on how long it's been since the last programming cycle. So everything is, if we have things that we're thinking about on the order of milliseconds, that's usually good enough on the EEPROM. So what we're going to do is whatever EEPROM operation we're performing, we're going to perform that operation, and then we're going to check to see if it's complete. But we're going to wait for a millisecond before we go back and check it again, because there's no sense checking it more quickly than a millisecond. And this is nice and generic, and that way we don't have to come in and say, okay, you know, well, if we're writing this particular thing, then we're going to wait 600 microseconds or 30 milliseconds or 900 milliseconds. By the way, 900 milliseconds is a long time. That's almost a second. That's forever. That's almost 2 seconds. So let's talk about how we're going to structure our EEPROM. Again, this is important stuff for us to figure out how to do things in the embedded world. How are you going to store stuff in the EEPROM? So we've got 2 types of things that we're storing. We're storing an event that has a light level, humidity level, or temperature level. That's part of what we're storing. But the other thing that we're storing is that we are also storing in this EEPROM, we're storing errors, error information. And so let's talk about how we might structure each entry in the EEPROM. So the first thing that you'll see that I have at the beginning of the EEPROM this thing that I call a cookie. And that can be a byte, it can be a word. Generally, it's a couple of words. And a cookie is a value that you can look for to see if the EEPROM has been initialized. That's basically what we're looking for here. So let's think about some values that might be good for a cookie. So all zeros, let's not talk about all zeros. Let's talk about all Fs first, so all ones. When you think about a EEPROM, one of the things that you should know is that when you erase a EEPROM, all the cells go to all ones. So an erase of almost all permanent program memory, when it erases, it goes to a 1. That is an erased state. So if I set my cookies, if I were to set my cookie to all ones, then the moment I go in and read an uninitialized EEPROM, it's going to look like I'm going to see that cookie there, and I'm going to assume if it's FF, we're going to assume, hey, looks like we're all initialized. That's dandy. So one of the interesting things about a EEPROM is that is something that you don't think about, but you should, and that is that I can write to a particular memory location in EEPROM as many times as I want to. And by the way, the same is true for flash memory, because what a write is that a write basically is changing particular 1 bits to a 0. So if I want to write a different value, as long as I'm only changing 1s to 0s, I can very successfully write to a EEPROM entry that has already been written. Pretty cool. So what that means, though, is that if I want to invalidate my cookie without having to erase everything in my EEPROM, I could write a 0 out to the cookie. So 0 is probably not a good idea for a cookie. So I might pick a value like 85. I might pick a value like 23 hex. I might pick a longer one that is my mother's maiden name in ASCII. It doesn't really make any difference, except one of the things that I can do about do with a cookie, let's say that we're writing a program and we don't necessarily have all the requirements down when we start writing this program. And so let's say that normally, that when I created this thing, my EEPROM had the light level, humidity level, temperature level, if it's a particular log entry, and if it's, what you see described there. But let's say that Dr. Morgan came in and said, hey, I also want you not only to be able to log errors and light levels, but I also need you to be able to log lightning hits that you detect by seeing a particular I/O pin toggle. Well, I don't really have any place to put that, so I'm going to have to come up with a new format for all of my entries in here, which means that once I add in that code that has the lightning format, if I put that on a device that already has EEPROM storage for something else, now what I have doesn't, what my code is expecting in all those locations doesn't match what was initialized in there. So one of the things that I can do is I can change my cookie so that I can go out and look at that cookie and say, oh, the stuff written in here was for a different version of the code. Now I know I need to erase it or interpret it differently or do whatever. So that's another function of a cookie. So the next thing I'm going to put in my EEPROM is I'm going to put a start index that, much like we're really treating this a little bit like a circular queue here. So I'm going to have this start index that points to the very first value that I'm going to write to, or the very first value in my EEPROM. So when I start off, it's just going to point to the first record. Then I'm going to have this next index that I'm going to have pointing to the next empty record in the EEPROM. Now, one of the nice things about that, so let's say that I filled up my EEPROM, okay? I can now do a circular queue. So if I filled it up, I went down and my empty blocks were all the way down to the end, and then finally my empty block is pointing to this guy. I write something here, and then that's, even though there's information here, I'm going to treat that as my next empty block, and the start index is going to point to the next valid thing. So if I were to write into this record right here, okay, so that's my next index, go right into that record here, I'm going to increment my next index to point to there. But since the start index now is equal to the next index, I'm going to have to increment my start index, which says, you know what, this data is not valid anymore. So let's talk a little bit about the kind of information that I put in here. And file name. So maybe these are just bytes or words or something. So this is think of this as a union. Depending on what log type says, it's either this information or that information. One of the things that we can create macros when we're creating error messages that have a file name and the line number and then some sort of an error number associated with things. So I might assign numbers instead of that to my file names, or maybe this is going to be big enough that I can have my file name in here. But that makes it really nice when I get ready to go off and debug by logging from the C file, from the line of code that threw the error. I can log exactly where that happened. So that's actually more information than just that you had error XYZ. It says that you had error XYZ while executing the code in this particular location in your C file. So I think we have been doing about an hour with some pretty intense stuff. I want to go ahead and stop here. We'll pick up on this on Wednesday. We'll talk about the health task and some other stuff. Are there any questions? I know that you guys have got homework assignment that's coming up. Are there any questions about the homework assignment we need to address while you got me here? All righty then. Well, I will see you guys on Wednesday. Have a lovely day, and tell them I don't want it to rain on Wednesday in College Station. We'll talk to you later.